In this video, we'll be talking about the truth value for a single proposition and ultimately how to construct a truth table for propositions. So the first step in all this is to figure out how I determine the truth value of a complex proposition or a single proposition when I at least already know the truth values of all of the simple propositions out of which that complex proposition is made. And so the process here is actually fairly straightforward. So the rules for this are fairly straightforward, but it presumes you already have the proposition written out in symbolic form. Once you have it there, then you simply walk through these following steps. So the first step is to enter the known truth values for every simple proposition in the complex statement immediately below each statement, and then fill in around it with all of your operators in parentheses and brackets. The second step is to compute the known truth value for each lesser complex propositions. That is all the stuff in parentheses. And what this means essentially is you will have to determine what is called the order of operations. So you know precisely which piece comes first in the computation. And then finally, you use the last completed line of the main operator to compute the truth value for the entire proposition, and then you just enter that below, and then you know the truth value of that statement. So the easiest way to do this and to explain it, frankly, is to just start in on examples. But before we can do that, it is really important that you know inside and out all of the basic truth tables for your individual operators. You need to know exactly what it means when you have a negation, a conjunction, a disjunction, an implication, and equivalence, and know exactly what the truth values are for any possible situation. If you don't know your basic truth tables here, everything else in this class is going to be very difficult from this point forward. So let's start walking through some examples. In these examples, what we're going to do is just assume a couple things. First, in the examples given, we'll have the propositions written out in symbolic form with capital letters as placeholders for simple statements. And if you see an A, a B, or a C, then we'll just assume that those are true statements. And if you see an X, a Y, or a Z, we're going to just presume that those are all false statements. Now, of course, this is just a tool we're going to use so that we understand the process. We will eventually look at an actual example of a statement given in ordinary language and see how we can convert it into symbolic form, and then finally run through the process based on our own knowledge of the truth or falsity of the various statements. So let's start with a fairly simple example of a complex proposition and then see how we would go about determining the truth value of this entire statement. Now the statement itself reads A or if X and B, and the first step here is to simply substitute the known truth values of each of our simple propositions and then rewrite the entire formula with those truth values stated. Now remember, A, B, and C we're going to just pretend or assume are true, X, Y, and Z are false. So all we want to do is rewrite the formula with true or false stuck in instead of the various letters we're using, A, X, and B. So instead of A or if X and B, we get true or if false, then true. So the next step in all of this is to determine the order of operations for our proposition. And this is an extremely important basic idea for understanding all of this. In the end, I need to figure out the truth values of each and every operator in the statement. And the order of operations tells me which thing I have to do first. Where do I start solving for this entire equation? And for the most part, what you need to do is just solve all the stuff in parentheses first. If we look at this particular example, the entire statement as a whole is in fact just a disjunctive proposition. That is, it's an either or claim with two different disjuncts. On one side we have the letter A, and on the other side we have as a disjunct the entire conditional statement. And of course, notice that means before I could solve for the truth value of this disjunctive statement, I would need to know the truth value of the conditional statement first. At this point, I only know the truth values of X and B, And the next step is to figure out, well, what does that tell me? If I know that X is false and B is true, what does that tell me about the truth value of this particular conditional statement? Once I know this, then I'm in a position to solve for the truth value of the entire disjunctive statement. So my order of operations would begin by solving for the conditional statement. And this is something I like to do. You don't have to do it if you don't want to. But if you just write a little number to identify which things comes first, which comes second, what comes third, and so on, it's a pretty useful way of sorting out exactly what order you need to go in order to determine these things. So put a little 1 over the conditional statement to show that you need to solve for that before you can look at the disjunctive statement. And of course, the second step is going to be the disjunctive statement itself. So my order of operations is to begin by solving for the truth value of the conditional statement. And once I know if that conditional statement itself is true or false, then I'm in a position to determine the truth value of the disjunctive claim. So the next step is to simply solve for these operators in the proper order given using the appropriate truth tables for those distinct operators, and then simply entering the truth value underneath each operator step by step as you go. So we need to begin with this conditional statement. If I have a conditional statement where the antecedent is false, but the consequent is true, what do I know? So what we need to do is simply go to our truth table for conditional statements and find the appropriate line that we're talking about. What do we know about a conditional statement when I have an antecedent that is false and a consequent that is true? And of course, what we know about those kind of conditional statements is that they must be true statements. And so we simply write a true underneath the particular operator for that part of the complex statement. And then simply fill in the rest of the lines so that we know what we're looking at. Notice now what we have is just our disjunctive statement, which is the second part here, the second piece of our operators. And what we have basically is a disjunctive statement where both pieces are true. It's true or true. And so now we want to basically figure out, what do we know? If both my disjuncts are true with the disjunctive statement, what do I know about the truth value of that claim? Well, if we go to our truth tables, when we have a disjunctive statement that is true on both sides, we discover that it must be a true statement. And notice we've run through every piece of the puzzle. Every single operator in this entire complex statement has been solved for, and that means we now know the entire truth value of the statement. The statement A or if X and B, assuming the truth values we have plugged in there, that A is true, X is false, and B is true, this must be a true statement. And so typically, once you've solved for all this, you simply circle the truth value of this at the bottom to identify the total truth value of that original statement. And again, what this shows us is that this original statement, assuming the truth values that we have are correct, must be a true statement. So let's take a look at another example. This example says X or not Y if and only if A. Once again, the first step is to substitute the known truth values of all of our simple propositions in this statement, and then rewrite the entire formula with the operators and parentheses all in place. So in this case, remember X, Y, and Z are deemed to be false. A, B, and C would be true. And so what we want to do is simply write the truth value of each simple proposition down and then fill in everything else so we get F or not F if and only if T. The next step is to determine the order of operations for these various operators. And of course, notice that the end game here, the thing we're aiming at, is once again just a disjunctive statement. I have F on one side or X on one side, and then I have not Y if and only if A as another disjunct. But of course, in this case, I need to solve for the if and only if, but before I can do that, I need to know what this negation does for me. So the very first thing I have to do is solve for the negation. And then once I've solved for that, I can determine what the truth value is of the biconditional of my if and only if claim. And then finally, I can determine the truth value of the entire statement as a whole, which again is just a disjunctive statement. So once we figured out the order of operations, the next step is to solve for all of these operators in order using the appropriate truth tables, and then entering underneath each of these particular operators, so our negation, the biconditional, and the wedge, we need to basically stick in the truth value once we solve for the truth value of those operators. Now, the first place to start, once again, is with the negation. And these are, of course, always very simple. A negation just does the opposite. So if the original claim, y, is false, and I have it negated, then the entire statement simply becomes true. So if I have a false claim, it becomes true with the negation. And so I want to put a true underneath the negation symbol, or the tilde. And then fill in everything else. So instead of not f, I have a t as a substitute for that original operator. And then I just need to plug in everything else so that I have f or t biconditional t. The next step, since it's number 2 here, is to figure out what the biconditional has to say. And what I have is true on both sides of my biconditional. So we need to go to the truth table for a biconditional, and remember that a biconditional will be true when both sides are the same. It will be false when they do not match. In this case, they're both the same, so we know it must be true. And so we just want to stick a true underneath the biconditional operator symbol, and then fill in the blanks. So essentially what we're left with at this point is a disjunctive statement where I have false on one side and true on the other. And so I now need to figure out, as a final step here, the third operator, I need to figure out what the truth value of such a disjunctive claim would be. And if we go to our truth table for disjuncts, when we find false on one side and true on the other, we know that it's going to be true. And in fact, the only time a disjunctive claim will be false is if both sides are false. So we discover in the end that this must be a true statement. So again, the last step is to simply circle that truth value so you know that you've solved for it. And what this shows us essentially is that this original statement, x or not y if and only if a, that this entire statement, assuming the truth values that we've given are correct, is in fact true. So let's look at one last example here. And in this case, what we're going to do is start with a statement, a complex statement that is given to us in ordinary language. So our first step would have to be to convert this into symbolic form. And once we have it stated in symbolic form, we can use our own knowledge of the various simple propositions and their truth values to determine the total truth value of the statement as a whole. So we can see how this actually works in a real context. So this proposition basically says it is not the case that if the Beatles wrote Sympathy for the Devil and the Rolling Stones wrote Hey Jude, then John Lennon is dead and Mick Jagger is alive. Now, stated formally, we're negating this entire statement, so we get not if B and R, then L and M, where B and R and L and M function as my antecedent, respectively, and my consequent of this conditional statement, and this entire conditional statement is being negated. So the first step in all of this is to substitute in the known truth values of every simple proposition, assuming, of course, that we know them, and then rewriting the entire formula with all of the operators and parentheses and brackets in place where they belong. Now, the truth values of these should be fairly simple to sort out if you know anything about the Beatles and the Rolling Stones. The first claim, of course, that the Beatles wrote Sympathy for the Devil is simply false. Rolling Stones, of course, did not write Hey Jude, but John Lennon is in fact dead, and Mick Jagger seems to be still alive at this point. The next step here is to determine the order of operations. Now, in the end, this is just a gigantic, messy conditional statement. And each side of the conditional statement, the antecedent and the consequent, are simply conjunctions. So we would need to solve both of those conjunctions before we could determine the truth value of our conditional statement. So I put 1 over each of those because it doesn't really matter which one you do first. You just need to do them both. The second step after we've solved for both of those is to deal with the conditional statement. But of course, notice the end game here, the final point, is to negate the entire thing. And so the last step is actually to deal with the negation or the tilde. So the next step, of course, is to just start solving for all of this, plugging in the truth value of each of the various terms as we go through them in order underneath each of the operators, and then just continuously filling in the gaps with our operators in the basic formula of the entire statement. So we can start here. I have an AND claim, a conjunction. That needs to be solved for before I can deal with the conditional statement. And of course, a conjunction where both sides are false would have to be false. In fact, if you remember how a conjunction works, a conjunction can only be true if both sides are in fact true. So what we want to do is simply plug in the truth value of that conjunction, which is now false. And then we need to solve for the other one. The other conjunction has two true statements. And of course, if they're both true, this is the only time a conjunction is true. And so this conditional statement, number 2 there, is basically just a false to true, and the entire thing is going to be negated, which would be the third step. So what's the truth value of a conditional statement where the antecedent is false and the consequent is true? Now, if we run through the truth table, if you recall, the only time a conditional statement is false is if the antecedent is true and the consequent is false. But of course, what I get here is just the opposite. And that, of course, means that this statement itself is true. And of course, I want to put the tilde there in front of it because that's my final step. And so now we need to solve for this. If I have a true statement that has been negated, the result is fairly straightforward. Just do the opposite. So we end up with the false statement as a whole. What this shows us is that this entire original statement, the claim that it is not the case that if B and R is true, then L and M is true, assuming again the truth values we plugged in, which are actually at this point correct, that this entire original statement must be false. So the next step in all this is to figure out how to construct truth tables for single propositions. To this point, we've seen truth tables in use looking at individual operators where the different sides of each of our operators are kind of undetermined. But in this case, what we want to do is construct a truth table for a proposition that is complex where each of our simple terms are already given to us. Now, in the previous examples that we just went through in this video, the truth value for each individual simple proposition was already given to us, or we assumed, at least in those examples, that they were known. When the truth values are not known to us, we can nonetheless construct a truth table to show every possible truth value for any conceivable proposition, no matter how complex it might be. And each line in the truth table is going to represent one of the possible arrangements of all of the conceivable truth values for that particular statement. Now, the formula you will need to know to determine the number of lines that are needed in an individual truth table is basically this. L stands for lines equals 2 to the nth power. So L represents the number of lines that you will need in your truth table. N represents the number of terms or simple terms in the proposition as a whole. Now, what this means is that the number of lines you will need to construct a truth table for a simple proposition will grow exponentially with each and every addition of a simple proposition. So if I have one proposition, I would only need 2 lines. If I have 2, I'm going to need 4. If I have 3 different simple propositions in the complex statement, I would need 8, and so on. As you can see, the number of lines you would need starts to grow rather quickly. So let's take a look at this particular example and see how we would go about constructing a truth table to define every conceivable possible truth value for this complex statement. Now, the complex statement itself says it is not the case that P and Q are true or Q is true. Now, the first thing you want to do is set up lines like you see here drawn. You want to draw a line underneath the particular complex statement given to you in symbolic form, and then list on the other side of this line every simple proposition. In this case, there are only two, so I want P and Q listed off to the side as basically a way of recognizing how many different things I'm going to need to know. Now, since there are only two variables, P and Q, each of which could be either true or false, we find that we will need exactly 4 lines, and we'll get 4 possible combinations of truth values for those two different terms. Now, given that we only have 2 simple propositions in this statement as a whole, again, we will need exactly 4 lines to account for every possible truth combination that could be had for these 2 different terms. Now, the steps you go through to determine the truth values of everything is to follow very carefully a distinct pattern. Start with the first simple proposition, whichever one you have listed there, in this case P, and since there are 4 lines, you simply want to divide it in half, and on the top 2, in this case, you want to simply place true statements, and then on the bottom, what you want to do is simply place false. So however many numbers of lines you have, simply divide it in half. The top half will be true for this first term. The bottom half will be false. So the truth value for P in this particular case for the 4 lines is that the top 2 will be true and the bottom 2 will be false. And so now we move to the next term, which is Q. And what we want to do is simply divide this in half again, and then divide each half in half again. So if we take the top 2 terms, which is true and true, you simply want to divide that in half and put true on the top and false on the bottom. So notice for Q, the top 2 lines, we would want true and then false, and then follow that exact same pattern on the bottom half, so that in the third and fourth slot under the Q term, you get true and false again. So notice that in P, you get true, true, false, false. With Q, you get true, false, true, false. And this basic pattern is one that you're looking for. You want to do this every time the same way, and it'll just repeat itself over and over again. So the pattern you're looking for, the top half of the first term, you want all true. The bottom half, you want all false. And then with the second one, you want to take those 2 terms and simply divide them in half, and then just keep this pattern going, true, false, true, false. Notice what happens if we increase the numbers of terms that we have in our complex statement. If we have, for example, 3 terms, let's say P, Q, and R, we find that each of these can either be true or false. And so if we want to sort out every possible combination of truth and falsity between these 3 terms, what we have to do is start with our pattern. The first thing to note is when I have 3 terms, I need 8 lines in total instead of simply 4. So once you have 8 lines, what you're going to have to do is figure out what possible truth values could you have for these 3 terms together. And again, notice we have 8 lines because you can have all kinds of different variations here. I could have all 3 of them be true. I could have P and Q be true, but R be false. I could have P be true, Q be false, R be true. And you could just keep going all the way through until you have everything be false and so on. But what I'm going to need for 3 different terms are 8 different lines. And again, the pattern we're going to work with is you take the first line and simply divide the number in half. I have 8 lines, so I want to divide it in half, so I have 4 on top and 4 on bottom, and simply separate these so that the top 4 are all true and the second 4 are all false. And so we move to the second term, Q, and we want to keep this pattern going. Notice take the top 4 and divide it in half, so there's 2 on top and 2 on bottom. And take the bottom 4, divide it in half, so there's 2 on top and 2 on bottom. And then just transcribe so that you have true, true, false, false, true, true, false, false. And then again, keep the pattern going by just dividing in half with true on top and false on bottom. The final line, whenever you're finished, should always be true, false, true, false, true, false, true, false, all the way down. It should repeat itself like that invariably. The first line should be half and half. The last line should always be rotating, true to false. So let's get back to our original example, where we have only 2 terms, P and Q. Notice what we've done is solve for the truth values of every possible arrangement of P and Q. And we start by just putting true on the top two for P, false on the bottom two, and then the second term would be true, false, all the way down. Now notice what that's done for us is give us every possible combination available to us in terms of the truth values of P and Q. They might both be true, they might both be false, or one might be true and the other's false in either direction. But when we're finished, if we keep that pattern going, we get every conceivable truth value for those terms. Now the next step here is to simply transpose the truth values of those simple terms, P and Q, to the original statement directly underneath each of those letters. So notice that P, wherever you find it in the statement, is going to have two trues and then two falses in our 4 lines. Q will simply rotate, true, false, true, false. So go find in the original statement every single letter and simply transcribe underneath the truth values that you've assigned to these two different terms, P and Q. Now the next step in all of this is to identify your main operator and determine the order of operations for all of your functions. And of course, the main operator is essentially the operator that tells you what kind of statement this entire thing is. And in the end, this is just a disjunctive statement. It just turns out that one of the disjuncts is a complex statement itself. But in the end, the main operator has to be just this disjunctive claim. And of course, that means before we can determine the truth value of our disjunctive claim, we would have to determine the truth value of everything else on the other side. And before we could determine the negation there, I would have to know the truth value of this conjunction. So rather clearly, the first thing I need to do is solve for this conjunction, and then I can determine the truth value of this entire negation, because the negation is negating the entire conjunction. So once I know if the conjunction is true or false, I can simply negate it. That's step 2. And then, of course, we get our main operator, the wedge. So the order of operations here goes from the conjunction to the negation and then ultimately to the disjunction. And once again, this is a simple preference on my part. I think it's really useful to simply write a tiny letter above each operator so you know what order you're working in. This helps you keep things clear and orderly, and that's something that's often difficult to do with truth tables. Once you've figured out the order of operations, the next step is to simply walk through each operator in order, assigning the truth value to every conceivable line based on the truth functions that you've assigned to your simple terms. So the first step, of course, is to figure out what P and Q here in this conjunction under number 1 tells us. In the first line, they're both true. In the second line, I have one and true, one's false. The next is false to true, and the last is false and false. But it's an and claim or a conjunction. And so what we should know, if you know your truth tables well, is that the only time a conjunction is true is if they're both true. And we can see this by just running to the truth table for that distinct operator. Again, when I have a conjunction, whatever sits on either side of that conjunction, if they're both true, it's true. In every other case, it must be false. And so on the truth table, what you want to do is simply fill in the gap underneath the little dot there, the conjunction, with the appropriate truth value. In the first line, since they're both true, it must be a true statement. The second, I have one true but one false. That makes it a false statement. The next one, I have false and true. That makes it a false statement. And the last one, it's false and false, so it's false. So sitting directly underneath the dot, I should get true, false, false, false as a representation of the entire truth value of this single conjunction in this complex statement. Now notice what's happened here is I now have the truth value of the entire conjunction, which is true, false, 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 following the 4 possible slots that these truth values can go in. And of course, this entire conjunction, when we look at number 2 there, is being negated. So what I want to do is take that middle line that's still dark here, true, false, 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 and simply negate it and stick the truth values underneath that negation. And of course, with the negation, these are really simple. Take the original truth value and simply write its opposite. If it's true, it becomes false. If it's false, it becomes true. So the truth value you should have recorded underneath the negation is that the first line should be false and everything else would have to be true, because the original conjunction is true, false, 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 and I want the opposite there. Now notice what we've done by the time we've reached this point is what sits directly underneath the tilde is the entire truth value of this entire disjunct in the entire statement. Now, since the truth value for not P and Q is false, true, 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 the stuff that's still dark there, what's sitting directly underneath the tilde or number 2, the last step is to simply solve for number 3, which is our wedge or disjunct. And of course, I want to take the truth value of this entire disjunct, which is now identified by what's sitting underneath the tilde, and simply take those two terms with Q on the other side and see what it tells me. Now remember, with the disjunctive statement, a disjunction is false only under the condition that both terms are false. In any other possible arrangement, it has to be true. So if you look at the first line, we get false to true, the second line true to false, the third true to true, and the last true to false. That means that not a single one of these ends up being false, because the only time a disjunctive statement is false is if they're both false. So we want to simply plug in the final truth value, which would be true all the way down, true, 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 true. And that means that this original statement must be true in every possible situation. Now, of course, it doesn't always work like this. In fact, it rarely works like this. But what we've done is simply solved for the truth value of this original statement, not P and Q or Q, in every conceivable possible situation. If P and Q are both true, then we know this statement is true. If P and Q are both false, we also know this statement is true, and so on. So what this does is give us every conceivable truth value for this original statement, given every possible assignment of the truth values to the simple propositions. So let's take a look at a slightly more complicated version. This one says P or if Q then S. The first step in constructing our truth table is to simply draw a line underneath all of this and then separate out the original proposition from each of the separate individual simple terms. Now there are 3 terms in this argument as a whole, P, Q, and S, and we want to set them off to the left side there, and then we need to determine every conceivable truth value for these 3 terms. Now since there are 3 different variables here, P, Q, and S, and each and every one of these can be either true or false, what we have to do is simply run through our formula and figure out how many different lines we need. Now, since there are 3 variables, S, P, and Q, each of which could be either true or false, what we will need are exactly 8 lines so that we get every conceivable possible combination of truth values between these 3 different terms. So we need to start determining the truth value of these simple terms, and the place to start is with the first one, whatever you have written down there, and simply take those 8 lines, divide it in half, make the top 4 true and the bottom 4 false. And then you just want to keep dividing. So we have the top 4 are true for P, and we want to divide that in half and make the top 2 true, and then the next one's false, and then 2 true, and then 2 false. And then you want to keep dividing with the final one so that you get true, false, true, false, true, false, all the way down. So notice, if you follow this pattern and you do it consistently, what you will get is every conceivable truth relationship that could possibly exist between these simple terms. P could be true, Q could be true, and S could be true. Or I could have true, true, false, and so on. Every possible arrangement is given to us by simply following this pattern. And now we know the truth value in every conceivable instance for these 3 terms. So the next step is to simply transpose. Under P, we want to stick all 8 of the possible truth values in order under that letter, which is 4 true and then 4 false. Under Q, we want to stick all the truth values setting directly underneath that in the original term, 2 true, 2 false, 2 true, 2 false, and then under S, true, false, and so on. So we simply take all the truth values we've determined on the left-hand column there and transpose them accordingly where they belong. So the next step is to determine what our main operator is and ultimately figure out the order of operations we'd have to go in to figure out the truth value for this particular statement. And of course, the main operator here is simply our disjunct. This statement as a whole is nothing but an either-or claim, where on one side, one of my disjuncts is simply P, and the other is this complex statement, if Q then S. That's one of my disjuncts. So in the end game of all of this is to figure out what this either-or claim is doing. But of course, before we can do that, we need to solve for this if-then statement. So our order of operations is fairly simple. The first thing I need to solve is what's in the parentheses here. This conditional statement needs to be sorted out. That's step one. And then I can deal with my main operator. Once I know the entire value or truth value of this conditional statement, then I can determine the truth value of the either-or claim. So the next step is to simply go look at this conditional statement and using the truth table for a conditional statement, determine the truth value of all 8 possible lines. And notice at this point, all we want to look at is that conditional statement. We could ignore everything else in this and just look at Q and S, if Q then S, in every possible arrangement. So we want to know if Q then S, if Q is true and S is true, what do we know? If Q is true and S is false, what do we know? And so on. And so we go to our truth table for conditional statements. And if you remember, when you have a conditional statement, the only time it is false is if the antecedent is true, but the consequent is false. So we're looking for that particular relationship, and we want to just go stick in false wherever you find it, and then fill in true everywhere else. So notice the second line is a true to false, and that is going to be false. And then the third from the bottom there is also true to false. That would have to be false, but everything else would be true. So the truth value for this entire conditional statement would be true, false, true, 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 false, true, true. And you just want to write in accordingly based on the antecedent and the consequent for each of these 8 individual lines, following simply your truth table. Now notice what's directly underneath the horseshoe there, the if-then, is the truth value of that entire statement. And that is what we're interested in. This is a disjunct for this disjunctive statement, which is number 2 here. And so I want to compare the 2 lines that are still dark here. Under P, I get true, 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 false, 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 false. And then under my horseshoe there, the if-then statement, I have the arrangements of truth terms. I want to simply compare these 2 lines as a disjunct. And of course, a disjunct, if you remember, is false only when both are false. It's true in every other possible arrangement. So pretty much what you want to do is walk through each line, all 8 of them, step by step, and look for anything that's both false and put a false there. Everything else has to be true. Well, in the end, there's only one part at the very bottom there, third from the bottom, where both pieces are false. Everything else is true. So I get true, 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 and then I get my false, and then 2 more trues. This is the total truth value in every conceivable arrangement for this original statement, P or if Q then S. So let's take a look at one last example. This particular statement says, if it is not the case that P or Q, then Q and S. Now, once again, we end up with 3 different variables, P, Q, and S. And really, the only reason we're not doing more is because the numbers start getting quite insane. If I had 1 more variable, I would need 16 lines. If I had 2 more variables, I'd need 32 lines. And things start to get really complicated really quickly. And frankly, I just don't have room on the PowerPoints. So we have 3 different variables, P, Q, and S, each of which could be either true or false. And so we need to simply determine the truth value for each individual simple proposition. Now, since there are 3 different variables, I need 8 different lines. And what I want to do simply is start dividing according to the rules that we've already seen over and over again. So in the first case, I take the first term P and I want to divide that in half, which means 4 on top, 4 on bottom, 4 true, and then 4 false. and then just keep dividing so that I get 2 true, 2 false, 2 true, 2 false, and divide again so that I get true, false, and so on all the way down. Now, once we've sorted out the truth values for each and every individual proposition, following this pattern consistently, the next step is fairly simple. Now we want to transpose the truth values of each of these terms respectively where they go. Under P, I want 4 truths and then 4 false. Under Q's, I want 2 true, 2 false, and so on. And under S, I want rotating true, false. And you want to just take what is given on the left-hand column for each of the simple propositions and place them directly underneath the letters that you're looking at where they belong. Now the next step here is to figure out what your main operator is and also to determine the entire order of operations for all these functions. And of course, in the end, all this is a giant conditional statement. It's just an if-then sort of statement. On one side, I have a negated disjunct as my antecedent. On the other side, I have a conjunction, Q and S, as the consequent of that conditional statement. But in the end, it's just an if-then, and that must be my main operator. Now, to sort out the order of operations, what I need to do is basically figure out each side of this conditional statement in order. So I might start with the consequent Q and S and just figure that out, and then move over to the other side, the antecedent. Now notice with the antecedent, I have to figure out what the truth value of the disjunction is before I can negate it, which is number 3. And then I finally know the total truth value of that entire antecedent. So the order of operations essentially is going to start with the dot, and then we move to the wedge, and then we move to the negation, and then finally the horseshoe. Now, the next step rather clearly is to just start solving things in proper order. Since I want to start in this case with the and, I just need to look at it and it alone and then figure out the total truth value of that sort of a claim given every possible truth arrangement between the terms Q and S. So we need to focus our attention just on that conjunction and nothing else, where the truth values of Q and S are already given to us. And so we can run to the truth table for our conjunctions. And if you remember, a conjunction is true only if both conjuncts are true. In every other possible arrangement, if anything at all on either side is false, then it must be a false statement. So pretty much what I'm looking for as I wade through each of these individual 8 lines is I'm looking for any situation that's both true, and I want to put a true there, and then everything else has to be false. And of course, given the truth values of Q and S, what we find is that the first and the fifth line are the only ones that'll be true, and everything else would have to be false. So the total truth value here of our conjunction is true, false, 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 and then true, false, false, false. The next step is to move to the other side, to the antecedent. And before we can resolve the whole negation, we have to figure out the disjunct. So we have the disjunct P or Q, and we have all of the corresponding truth values for P and Q listed beneath them. And so now we need to go figure out what our truth table is for a disjunction, and then walk through each line individually to see what the truth value is for the statement on each possible arrangement. And again, a disjunctive claim will only be false if both terms are false. In every other possible arrangement, it would have to be true. So if we start walking through all of the possibilities, we discover that it's true all the way down until the bottom 2, where we get false on both sides. Each disjunct is false, and so it has to be a false statement. So we get 6 true and then 2 false for the total truth value of this disjunction. And of course, the next step here is to negate this whole thing, because I can't solve for number 4 for the if-then statement until I know the negated value of this disjunction. And of course, negations are really simple. With the negation, all you want to do is take the truth value of that term and swap it to the other side. If it's true, it becomes false. If it's false, it becomes true. And so now everything is false except for the bottom 2. And so finally, we're in a position to deal with our main operator, the if-then claim. And so notice what's sitting, all the truth values that are sitting directly underneath the tilde on number 3 there are what we're taking to be the entire truth value of the antecedent for this claim. And all the truth values that are sitting directly underneath number 1 or the dot are the entire truth values for the consequent. And so we want to take these two lines and simply compare them with conditional statements and all the possible truth values for conditional statements. Now, in a conditional statement, if you remember, the only time a conditional statement is false is if the antecedent is true and the consequent is false. Every other arrangement must be true. If they're both true, then it's a true statement. If my antecedent is false, but the consequent is true, it's still a true statement. And if they're both false, it ends up being a true statement. So what we're looking for is underneath the tilde anything that's true, which really just means the bottom two. And then it really doesn't matter what happens on the other side. So we find that the total truth value of this statement is everything's true except the bottom two, because the bottom two give us true to false relationships with the conditional. So this entire complex statement, if it is not the case that P or Q, then Q and S, is true in every possible arrangement except the bottom two. And so having gone through all of this mess, we now know the total truth value of this statement in every conceivable situation, given all the possible truth values of P, Q, and S together. So that covers the core ideas of dealing with truth tables for propositions. The next step is to convert all of this into using truth tables for determining validity in an argument, and that's where we'll be heading in the next video.